Newton's second law can also be used to develop a relationship between the force of gravity, which is Fg, and the acceleration due to gravity, which is little g. When I look at Newton's second law, it's F net equals ma. For an object in free fall, nothing is touching the object because we ignore air resistance, and we know that its acceleration is equal to negative 9.80 meters per second squared, or little g. So Newton's second law becomes Fg equals mg. When I look at that equation, what I'm really finding is the weight of the object. Fg refers to the weight. Sometimes you will see it written as Fw. I may do that sometimes in class because I'm used to using Fw, but because our textbook uses Fg, I'm going to try to stick to that. So Fg refers to the weight. The weight of an object is measured in newtons. Newton is the unit for all forces. A newton is a kilogram times a meter per second squared. The weight of an object, as you can see in the equation, Fg equals mg, depends on the mass, but also the acceleration due to gravity at your location. So your weight, or the gravitational force on your body, which is Fg, is going to change if you were to go to the moon. Mass, however, is a property of an object that does not change. It is measured in kilograms, and it will stay the same whether you're here or you're on the moon. One of the ways that we typically measure weight is to use a scale. And when we use a scale, what we are looking at is a free body diagram where Fg is the downward force, and most scales use springs, so we'll call this the spring force. So if I were to sum the forces, F spring is my upward, minus Fg is my downward, that is equal to my F net, and we know that F net equals mass times acceleration. So if I want to get the reading on the scale, which we'll just call the spring, the force of the spring, because when you stand on a scale, obviously the earth is pulling you downward, but there has to be something pushing back up. That's the springs on the scale. So if I rearrange this equation to be ma plus Fg, when you're standing on a scale in your bathroom, you're not accelerating. So my ma becomes 0 because of the zero product property. Whatever I multiply by a, which is 0, I get a 0 answer. So a scale typically reads your actual weight. So when you're standing on a scale, it's reading that force that opposes the force of gravity on your body, which we typically call the spring force. We will be using spring scales this year. Some of the scales in your home would be using springs. So we typically call that the spring force. However, what if the scale itself is accelerating? So if I take my equation, the spring force, which is the reading on the scale, is equal to ma plus Fg, then I could see how a scale could read something that is not my weight. So you're going to ask, how do you make a scale accelerate? One of the ways to do that is to put it in an elevator. And you're going to see some elevator questions in the sublevels. If I'm riding an elevator, whether it's moving up or it's moving down, at certain points in the ride, it's going to accelerate. If I have a positive acceleration, that means that the reading on the scale will be greater than your actual weight. If the acceleration is negative, that means that the reading on the scale will be less than your actual weight. So we're going to do a lab where you actually get on an elevator, and using a spring scale, you measure the weight of an object. It's just going to be a 1 kilogram mass. When we get a reading on a scale that is different than the actual weight of the object, we call that the apparent weight. So when we are measuring the weight of an object, we are actually not measuring the weight directly when we use a scale. We're measuring the upward force that opposes the weight. And as I said, when you're in your house, you're not accelerating. So that would be your actual weight. But if you put your scale on an elevator, you're going to see, because the elevator is accelerating, that there are points in the elevator ride when the scale reads either greater or less than your actual weight. So that brings about another question. If I'm riding in an elevator and the elevator cable breaks, what's the scale going to read? If a breaking cable, which is what holds the elevator up, would cause the upward force to disappear, if a scale reads the upward force, then the scale is going to read 0. So when you hear the term weightless, it doesn't actually mean that the object has a weight of 0. It just means that its apparent weight is 0. Because if you were in the elevator on that scale, and the top cable broke, there's no force there any longer. You're just in free fall. And in free fall, we remember that the only force acting on it is gravity. So that upward force would be 0. It does not mean that you've all of a sudden become weightless. It simply means that your apparent weight is 0.